Okay, so we just did a neat little calculation on kinetic energy. I'm going to go ahead and do this other one because it's really a good. I think there's a problem like this in your next exam, so it's important to do this one too. So we just did an example of kinetic energy, and that was an automobile going straight on the flat. So here's the car going that way. In this example, well, it's still box 8.2. So box 8.2 continued. What we're looking at is a car going uphill. Oh my gosh, it's a wild-looking car. Okay, so now it's overcoming gravity, and now we know that in the case of gravity, energy equals mgh. What's that mean? Well, as you could probably guess, the heavier, the more massive the car is, the more energy it's going to have. The stronger the gravity, so this is, different if you're on the moon or a solid planet with more mass. Does Jupiter is Jupiter a solid at all? Is there any solid matter? You keep saying, if I'm driving on Jupiter, but I don't think there's any solid. Okay, so forget what's that? I think it's completely gas. I don't think there's like solid up there. So don't be walking on Jupiter because there's nothing to walk. I
wonder how compressed into the core is, though.
Yeah.
The gas is probably so dense you could walk on it.
Maybe, yeah. Probably pretty hot, too.
I guess that depends on your definition of gas.
Yeah, it's gnarly. Anyway, and then the higher you get to, the more altitude you get, the more energy you have. Speaking of matter, I guess the Nobel Prize was just awarded for the discovery of a fourth or fifth phase of matter, sort of this, monolayer, and at that scale, these very thin layers of molecules are displaying this quantum behavior where they get a little tornado spinning up and then another one spinning down, and not unlike what you'd see on the periodic table with the electrons up spinning down. Cool stuff. We'll see if it goes anywhere.
Bob Dylan too.
Bob Dylan too.
Nobody saw that coming.
Is that in the
Literature.
Hadron?
No, the physicists are not. It's not high energy physics. It's pretty low energy actually. Low temp. Yeah. Okay. Now what we're going to do? Suppose the 1 ton car. So again, the car has a mass of 1. This is a metric ton. 1,000 kilograms. 1 ton car, 1,000 kilograms, is going to climb a hill. It's a 1 in 20 hill. I've drawn it pretty steep, but a 1 in 20 hill means we're going to go up 1 for every 20 we go over, and it's 100 meters high. 100 meters high, and it's going to go at the modest speed of 60 kilometers per hour. Now, the energy is going to be fairly straightforward, so we just know that E equals 1,000 kilograms times gravity. What do they use for gravity? Okay, they're using 9.81. You can throw 10 in there, but let's just use 9.81 since we're such a fan of 3 significant digits. And this is meters per second squared. And then we're going to multiply that by 100 meters. And note that I'm putting the units in there. The book leaves them out, but I think it's important that we keep that in. So kilograms times meters per second squared times meters. And what do we end up with? I'm going to write that out again as joules. So 981,000 joules equals 981 kilojoules. Okay, same question. How long is it going to take you to pull that car up the hill with your 100 megajoule per day self? Little in-class calculation for you.
2 hours.
Yeah, double, right? Because before we looked at .45 came out to be 1 hour, so we approximately double. So it's going to take you 2 hours to pull, and you're going to end up lock and tackle because you're not going to have enough power to keep it from running you over, unfortunately. But on that note, let's now go from energy to power. So it said that it took this car 2 minutes. So here's, last time I said that, time is typically the independent variable, space sometimes is, sometimes not. But you can sort of look at this distance travel as also just a little mini time travel. So it took me 2 minutes to get up here. That equals 120 seconds to get up to the top of the hill. So I'm sort of drawing time in a vertical axis. And I know that power equals energy divided by time. And the energy is 981 kilojoules divided by 120 seconds equals, what's that come out to be? 8.2, I'm just copying from the book, 8.2 kilojoules per second equals 8.2 kilowatts. Okay, so how many human powers is that? Remember the human power was 113 watts. So let's just run that. We'll see how many friends you would need to pull that car up the hill. So 8.2 kilowatts is 8,200 watts. 8.2 kilowatts is 8,200 watts divided by a human power. Let's say you're having a really good day and you're going to go at 200 watts. Because you can sustain, if you went out and started running through the parking lot right now, you'd be at 200. So let's divide it by 200. 41 people pull that up the hill. How many horsepower? Well, let's see. 8200 divided by, what do we say, 746 equals 10. So you could get 41 friends or go find a pal with 11 horses, pull that car up the hill. That's the power of petroleum right there. I mean, this is the eye opener when you go back to that summary one. Like there's a lot of energy in there. Okay. Now we looked at kinetic energy. This is a graph of power because power. I'll go ahead and write this out. It's not in your book. I'll write this out. Power equals force times velocity. Force equals 1/2. This is for rolling friction. This is for aerodynamic friction. Equals 1/2 rho. This will not be on the test, but I'm just explaining the graph. 1/2 rho a v squared. So this says the faster you go, the more dense the air is, and the bigger you are. Oh, and I left out C. There's a coefficient here. And the sort of squarer you are, so 1/2 C rho A V squared, that's the drag force, pushing back on the car. So here's the car right here. So you're basically just pushing air out of the way, right? The car is, and it's moving with a velocity v. It's got some cross-sectional area A. If it's a Prius, the drag coefficient is 0.3. If it's a big truck, it's 0.7, what have you. That's why you're starting to see some of these Class 8 semis with the fairings on them in the back. Like, hey, well, if we don't have to push as hard if we can drop this drag coefficient C. So there's also a C going on here. The air has some density of rho. That's why Elon Musk wants to build the Hyperloop. He wants to just get rid of air entirely. Zero drag. There you go.
It's looking pretty good.
Yeah, yeah. And then he's going to take it and just bend it up, and then the rocket will take off horizontally and up vertically. Maybe. I don't know. That's my prediction. Okay, so the point is power equals the force of drag times velocity equals 1/2 C rho A V cubed. The whole point there is that the power is a function of the cube of the velocity. So that's why we're seeing these curves that are really taking off. The majority of it is this purple. The vast majority of the drag is just the air pushing back on the car. The tires themselves, it's roughly linear. There's drag inside the engine, and then you've got your stereo going, and your heater, and your windshield wipers, etc. So there's the total power. Okay, so hopefully that also gives you the distinction between energy and power. Perfect. Okay. One more example. I think this is our old pal Henry Ford. There he is. Took these, backyard projects and really overcame a lot. I mean, not only just did he, have to source all the materials for this thing, the tires, the metal, the lamp material, the engines, there's a lot of wood in here, there's glass. He had to overcome some tremendous labor problems too, getting people to just stand there and just smack the same bolt into the same hole all day long. But really ushered in the transportation age in for the world. So there it is. Anybody been to this museum in Michigan? It's pretty amazing. I went to grad school there and got a chance to check it out.
Glove box right there, that wood box?
This is your box of tools.
Oh.
Yeah, this is your box of tools because you're breaking down. And I don't see it, but up here somewhere,
The crank.
you're going to be your crank start. There wasn't a electric start on these guys, or probably was a rudimentary battery. That's where you're getting your lights from. Steam.
Toolbox.
Steam. Yeah, that's absolutely your toolbox.
They were super capable too.
Yep. Yeah.
Off the road, they did amazing.
Yeah. Yeah. So pretty
Ford
cool.
was the first to have an efficient assembly line.
That's right. Yeah, Ford is frequently attributed with inventing mass production on the assembly line. That's right.
And the working wage and 40-hour work week.
Yeah. Yeah.
It was brilliant. He was like, I have a product I want to sell, but
Yeah.
my employees can't afford it.
Right.
So I'll just give them more money and time to go play with it.
Yeah, and it's a chicken and egg problem. Like how do I allow my employees to afford it? And the same thing might be true. I don't know what's going on with the iPhone factories in Asia and all that, but
Oh, yes.
it's constant chicken and egg. It's the same thing. You see people who are working in the service industry, hotels, et cetera, cleaning rooms for people that can't afford it. It's the economy. For whatever it's worth. All right. Now we're looking at cars owned per 1,000 individuals, and you can see that the United States has reached just about parity. One car per person, including this is all 2 and 4. We seem to have peaked a few years ago. At one point, I don't know what was going on, but my father had 7 cars. He had a van, he had a thing he drove to work, another thing he drove out to the farm. It's just like, what is going on? The old station wagon. So U.S. car ownership peaked, French ownership peaked. It's intriguing to me that it's taken this long for the UK to sort of catch up, if you will. It's intriguing. Okay, so enough about cars. The next thing, aircraft petrol engine. There's a supercharger that's mentioned, engine-driven pump which compress the air before feeding it in. So if you remember the figure there, if you can basically jam more air into the chamber, you're going to have better stoichiometry. You can also jam more fuel in, sort of more bang for your buck per revolution. That's what the supercharger is. There's also a turbocharger, same thing. So the exhaust gas is coming out, spins something that just shoves air through the engine faster. Otherwise you're just sort of allowing whatever suction or Venturi effect is there to do it. So that's aircraft, petroleum engine, and aircraft engines. Not exclusively turbine engines. If you go look at some of the World War II engines, they're reciprocal. All of the cylinders are in a circle. Some of them are sideways, some upside down, which presents its own challenges. Operating that in gravity. I had a chance to go down and be part of the Wright brothers celebration. It was like, oh look, the cylinder is upside down, but still working. Alternative fuels are mentioned here, and liquefied petroleum gas. It's mainly propane and butane, so just lighter than octane. The energy density of those two is greater on a per mass basis, but not on a per volume basis. That's why octane tends to win. Lead additives are mentioned, and if you want to see something extraordinary about, so if we look up Neil deGrasse Tyson, lead, was it Cosmos?
That was a really great.
Did you see it?
With the investigation of the age of the Earth.
Did you see it?
I did see it. It was really fast.
Yeah, and like these two things you would never put together. Never, but there's a scientist, and this guy was, and I'm not going to take any more time, but just to explain it, this scientist was curious about the age of the Earth, because if you know that, then you can start to date how old some of these petroleum reserves are. Where does zero start and where are we now? And a lead isotope was used in that, and of course he's being funded by the petroleum industry because they want to go get more petroleum out of the ground. And the lead isotopes that were in his laboratory the numbers were all over the charts. One day he'd walk in to be high, the next day it'd be low. He's like, why, what's going on? It's the same sample. He himself, walking back and forth into the lab off the streets of Los Angeles or Pasadena, where he was dragging more lead into the lab than he had in his vials in his lab. So he had to invent the clean room, strip down, take his clothes off, whatever, get in a garment before he could actually get his measurements accurate. He's like, oh my gosh, there's more lead being sprayed out of these, giant Cadillacs and all, these huge cars of the 70s. There's more lead on the streets of California right now than I'm digging out of these ocean samples and what have you. Wow. So, and then all of a sudden, these things start coming out. Lead poisoning, but meanwhile, the gasoline manufacturers are putting lead into the gas as a lubricant. Lead is a fantastic lubricant. So, it's going in there so the engines last longer. And all of a sudden, wait, we've based all of our technology on leaded gasoline, and you're telling us that there's more lead? So it was this big controversy, and he had to testify before Congress to get lead taken out of gasoline because...
Yeah, they fought it, too.
They fought it. People were getting dumb. It was. I mean, that's one theory as to what took out the Roman Empire.
A satellite going down in the background.
Oh, yeah. Yeah, it's funny, you just kind of have to deal with that stuff. Yeah, so anyway, if you just kind of want an interesting chunk of history, you might check it out, because I think we're going through similar issues with carbon dioxide. All right,
That's crazy that Brad would bring it in and.
we're just dragging it in. Yeah. Yeah.
Contaminate his own
Yep,
samples.
absolutely. Same thing happened on the first lunar landings. They were trying to measure atmospheric pressure on the moon, and it was purely a function of how far you were from the spacecraft. It's more air coming out of the craft than there was in the first place.
Wow.
Yeah. All right, quick break, and then we'll finish the chapter.